All right, today we're going to break down a really fundamental principle in electrical engineering. It's all about how you get the most, well, bang for your buck out of any power source. So let's jump right in.
Electro knowledge. Power up your concepts.
Okay, so let's start with a really core problem. Imagine you've got a power source. Could be anything, right? A battery, a big generator, even a solar panel. The question is, how do you design your circuit to pull the absolute maximum amount of power from it? It seems simple, but it's a puzzle that engineers have been working on for a very long time.
You see, the key to solving this puzzle is understanding one crucial thing. Every single real-world power source has some kind of internal resistance. We'll call it RS. You can think of it like internal friction. It's just an unavoidable part of physics that's always there, and it wastes some of your precious energy as heat before it can even get to the part of the circuit that's doing the useful work, your load.
So how do we work around this pesky internal resistance to get the most useful work done? Well, the solution is actually pretty elegant and surprisingly simple. It's called the Maximum Power Transfer Theorem. This idea has been around for a while. It was first described by a guy named Moritz von Jacobi way back in the 1840s. What his theorem does is give us a very precise mathematical rule for hitting that peak power delivery in a DC circuit. It basically tells us exactly where the sweet spot is for our load.
And here it is, the absolute core of it in all its simplicity. If there's one thing you take away from this, let it be this. For maximum power transfer, your load resistance, RL, must be equal to your source's internal resistance, RS. Not a little higher, not a little lower, it has to be a perfect match. That's the rule.
Okay, I know that might still sound a bit abstract, just talking about RL and RS, so let's make it really concrete. We're going to walk through a quick example with some actual numbers to see exactly how this plays out and prove that this matching thing really is the key. All right, so let's imagine we've got a power source. We know it has an internal resistance of 0.8 ohms. Our whole goal here is to pick the perfect load resistor to connect to it, the one that's going to draw the most power possible. So let's test a few different options and see what happens.
Okay, first up, let's try a load resistor that's too low, say 0.5 ohms. What happens? We get 37.2 watts delivered to it. Not bad. Now, what if we go too high? Let's try 1.1 ohms. Okay, we get a little more power this time, 38.2 watts. But here's where the magic happens. What if we choose a load that is an exact match for the source's internal resistance? 0.8 ohms. Bam! The power delivered to the load jumps to its peak, 39.2 watts. See? It's highest right when they match.
Now, this is where things get really interesting, and it's probably the most important part of understanding this theorem. You see, getting that maximum power we just saw, well, it comes with a pretty big and often misunderstood trade-off.
You know, there's this very common myth that if you're getting maximum power, you must also be getting maximum efficiency. It just seems to make sense, right? But it's not true. In fact, it's something engineers like Thomas Edison figured out back in the 1880s. Power and efficiency are two completely different goals.
So get this. At that exact sweet spot, that point of maximum power transfer, the efficiency of the circuit is only 50%, exactly 50%, not a bit more. And why only 50%? Well, it's actually pretty logical when you think about it, because when the load resistance equals the source resistance, the voltage drop across them is the same. That means the power being generated by the source gets split perfectly in half. Half of it goes to your load to do useful work, but the other half, it's just wasted as heat inside the source itself. This really lays out the two different worlds we're talking about. On one hand, you've got maximum power transfer. The condition? You match the resistances. RL equals RS. The result? 50% efficiency. On the other hand, you have maximum efficiency. Here, the goal is totally different. You want your load resistance to be way bigger than the source resistance. You'll actually get less power at the load, but your efficiency approaches 100%. And as you can see, the applications for these are worlds apart. So this brings us to a really important design question. With this trade-off in mind, when do you actually want to design for maximum power, and when is efficiency the only thing that matters? It really all comes down to context. You want to use max power transfer when you're dealing with very low power signals. Think about a radio antenna or an audio amplifier driving a speaker. The total power is tiny, so you want to squeeze out every last drop to get the strongest possible signal or the loudest sound. But you would never do this when efficiency is the name of the game. Think about the electrical grid. A 50% loss there would be an absolute catastrophe. We're talking about wasting unimaginable amounts of energy and generating so much heat it could literally melt the equipment. And just so you know, this whole principle isn't just for simple DC circuits. It extends to AC circuits too. The core logic is exactly the same. But instead of just talking about resistance, we have to talk about impedance. The goal is still to match the resistive parts, but you also have to cancel out the reactive parts, the inductance and capacitance, by making them equal and opposite.
So what does this all boil down to? When you're designing a system, is it better to be powerful or to be efficient? The Maximum Power Transfer Theorem teaches us a really important lesson. There's no single best answer. It forces every engineer to make a fundamental choice. Do you need the absolute most power you can get, even if it means wasting half of it? Or do you need to be as efficient as possible, even if it means you get less power overall? The answer? Well, it depends entirely on what you're trying to build.
Thanks for watching. Like, share, and subscribe to Electro Knowledge for more electrical concepts.